Welcome to another video using the particle model to explain the universe. Well, today's video is about the light emitting diode. And it was just recently a video that I released before this that I talked about the diode itself. And you can view that video at this link. Two other videos that I've made in the past that relate to this in terms of light is the video on the candle and the video on the light bulb. So it helps if you review some of these before you move on with this one. Okay, so the light emitting diode is the light in it is produced by the recombination of electrons and electron holes in a semiconductor, a process called electroluminescence. The wavelength of the light is produced depends on the energy band gap of the semiconductor used, at least. That's the standard explanation. Here's an example of an LED circuit with a DC supply current flowing through the LED diode. That's the symbol. Usually see light type. It looks like lightning coming out of the diode. And then there's the current limiting resistor. And the diode is actually forward biased. And more explanation, the free electrons in the conduction band releases energy in the form of light before they recombine. Now, it's an interesting comment. I'm not exactly sure what that means. Before they recombine with the holes in the valence band. And the material for the diode is different than the regular diode I talked about. The last time that I said the diode typically was silicon or germanium. In this case, the material is gallium arsenide or gallium phosphide, and the emitted photons have sufficient energy to produce intense visible light. So a lot of this has to do with doping, and all I can do is tell you what they say because I'm not an expert in how diodes are doped. And I mentioned IV curve for diodes last time, and this is a typical one. And again, here's the symbol for a diode showing light being emitted. This is a typical way that it's packaged. And the IV curve is forward biased, and so it uses this first range here, where the current is in the range of 20 to 50 milliamps and the voltage from 1 to 5. What is interesting about this is they're showing the different colors, and it appears that the colors are dependent on the forward voltage, and yet they said it was dependent on the band gap. Maybe there's a correlation there, and I don't dug into that, but you have anywhere from infrared all the way down to blue and white. Now this is the physical structure of a diode. It has a lens, and when an LED is on and lit, high intensity, this LED can get hot. The anode, the positive side, where it shows the arrow, is bonded down into this cup, bonded to the diode, which is here, and then the cathode comes back out the other way, and you have your connection. And it's interesting for 2 points here. Number one, the light is shown going out in all directions, but still they use a reflector cup such that some of the light may hit the side and bounce out differently. But the intent is that the LED is visible from all directions. That's different than a laser. This is not a laser LED. This is just a normal indicator type LED that we see on circuits and electronic equipment all the time. Okay, so let's talk about recombination. I was kind of surprised at that one just recently when I read that. Uh, but let's look at the diagram. This is a light emitting diode with the positive end of the battery tied to the p-type, and the p-type is doped one way, and it pushes holes. And the negative side is connected to the n-type, where there are more negative charged electrons, and so the negative repels the negative and pushes the free electron this way. And by the way, holes are supposedly positive, although holes are nothing. And how in the world you push nothing is a little bit curious. But you can see here where the electron and the hole recombine and emit the photon. Just but anyway, the hole is nothing, but what really happens in my mind is the electron fills the hole. That's what happens. There's no pushing of the hole. The electron moves this way, and it it goes into an empty space where it can exist, and therefore, yeah, it recombines. Well, this is a slide that I showed in I think in both of the videos on the candle and the light bulb. And it explains how atoms emit light, and it gives 3 steps. And I know you can't read this, but let me just talk you through it. In this case, a particle hits the nucleus or hits something and excites the atom, causes an electron to jump. In my version of recombining, it leaves a hole behind. And later, for whatever reason, it decides to fall back into the hole, recombined with the hole, and emit light. So those are the 3 steps. The particle collides with and excites the atom. The electron jumps to a higher level. It falls back, releasing energy in the form of the photon. And of course, as I've said many, many times, energy is not real, and therefore I don't see how it can actually make a photon. Just doesn't make sense. Okay, the particle model for the LED. This is the same circuit, similar circuit before, a 9-volt circuit with a 1K limiting resistor, giving you 9 milliamps of flow through the LED. That's an LED because it's got the light shown. But the G1, in the particle model, G1 flows the other way. Forward bias is determined by the G1 flowing into the cathode. That's what I've shown over here. This is a diagram that shows the LED forward bias. It's not because of plus and minus. It's the direction of the flow of the G1. And when it's forward bias, it has to overcome this force. There's a net force pushing backwards. So in a sense, it doesn't get much flow when it's having to overcome it. But once there's enough, then the G1 particles flow through. And that's forward bias. But as opposed to the atom being excited, unless your term for excitation in the atom is a vibrating atom, because as the G1 passes through the LED, they hit the atoms and they start vibrating. They heat up. The more they vibrate, the more the heat, and the LEDs get hot. But it's this vibration that's important. When the atoms in the LED vibrate, they push clumps of G1s, the G1s that flow through in a repetitive pattern that is in the visible spectrum. They have to vibrate at the same rate. If you want, for example, a red LED, it's got to vibrate that way. This is a standard model that I've shown for light, showing G1 particles flowing to the right here at speed c. You have a clump here and a clump here, which define the peaks, and you have very few G1s here define the valley. And you can make sine waves, square waves, triangular waves, pulses, using this concept of particles. So you get a stream of particles being pushed by the vibrating atom here, pushing out a clump, and then later pushing out another clump. So they, in fact, you can push the other way when the atom retreats backwards. It's pushing light out the other side, a clump out this way. Interesting. Forward clump and a backward clump, if you will. And a red LED must light from it must have most of the streams in the same pattern and in phase. If you're going to see red, when the red hits your eye, you need to have a consistent pattern. Yeah, there can be other stuff there, but majority of the streams will have a peak that peaks spaced at the wavelength of red. And right now I'm just showing this bar to show that a bar like this, a long line, represents two or more peaks, because when you look at white is a mixture of all colors. And these represent streams of G1 particles that have peaks that are separated by a wavelength that is blue by red and green. G1 particles do not have color. In fact, nature itself is colorless. Color only exists when light, visible light, hits your eye and your brain tells you what the color is. Otherwise, nature is, I'm not even sure nature is white and dark, because nature doesn't see its own light. But this is the white light that could be generated from an LED. Not by the recombination, not by energy, but by vibrating atoms pushing out G1 particles. The standard explanation uses energy to make photons, but energy is not real. The particle model, G1s flow through the diode and cause the atoms to vibrate unless the LED gets hot. The vibrating atoms move forward and push out G1s to form peaks, and when the atoms retreat, only a few are emitted. However, you can be pushing out peaks the other way. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.